present is related to that. I acknowledge my collaborators, Dr. Shraddha Sharma, who became doctor just on 27th, and Uma Divakaran, who was my student now at CBS Mumbai, Anatoly and Sain, long-term collaborators, and Utsho, who should be there in the audience by compulsion, not by will. Anyways, these are the papers, one with Anatoly and Uma. That is what I'm going to present here mostly. And you have heard a lot of what happens after the quench in a closed quantum system, especially in Diptiman's lecture, and also Ornov-Shen this morning said many things about that. For example, linear growth of entanglement entropy following a quench, that is the famous Calabresi-Cardy work, and one can show that it is related to actually collapse and revival of the so-called Loschmidt echo when system is quenched to the quantum critical point, and these are all related to light cone-like propagation of quantum correlations, which has been experimentally seen, establishing that there is a maximum group velocity, so-called Lieb-Robinson limit. Diptiman also talked about thermalization, and there is also a plethora of studies on statistics of work done, because work done in a quantum system, work is not an observable, so you have to look at your distribution, and that is also related in some sense to the Loschmidt echo, which I mentioned. And of course, there is an upsurge in studies of periodically interval quantum systems in the context of periodic steady state, whether system hits up to infinity or not, or also in the context of entanglement or entropy, which Ornov said in the morning. What I want to present here in this talk, you just quench a quantum system and follow its real-time evolution, which is completely unitary, and see whether something interesting happens. Okay? So this is the two limiting quenching cases that those have been discussed by Diptiman and Ornov. You start from an initial state, which is the ground state of the Hamiltonian, say Hi, suddenly quench Hi to Hf. That means you have changed a parameter suddenly. There is something called Loschmidt overlap, which you calculate, which is nothing but your evolved state and inner product with the initial state you started with, and you define something called rate function. Why it's called the rate function, you will soon understand. And then this rate function is given by the log of the quantity in blue, which is the Loschmidt echo. Okay? Now this involves a double quenching process. First, you start from an initial state psi naught, you quench it, quench the Hamiltonian, not the state, because it is sudden, and then let it evolve, and you quench it back to your initial state. You measure how much of the initial state is still remaining in your evolved state, and if these two people are orthogonal, initial state and the evolved state, they are orthogonal, then you have this so-called quantum dynamical phase transitions. But I will be talking about slow ramping, which is interesting in the context of Dual-Zurich scaling, which was discussed at length. So you have an initial state psi naught. This is again the ground state of the initial Hamiltonian Hi. Now you change lambda I to lambda f, but through a protocol which is defined by a rate. For example, one could go like this, where this tau quantity defines the inverse of rate. Okay? Now you reach a final state, which is no longer an eigenstate of the final Hamiltonian, because there is a change in parameter, and if you cross a quantum critical point in the process, there will be definitely excitations. Now you set your watch and set the time scale t is equal to 0. Let the evolved state, I'm sorry, there is a mistake. This should be psi f. Psi f, let it evolve with the final Hamiltonian. Okay? You reach the state psi f and let it evolve with the final Hamiltonian, and look at the quantities like rate function of return probability and Loschmidt amplitude and see what you have. Do you have any non-analyticity? If it vanishes, you will immediately have singularities here, cusp singularities, and that is what people call dynamical phase transitions. But there are problems calling it a phase transition. You cannot define a local order parameter. Nobody knows whether there is universal exponents. Yes, please. This one here, there is a typographical error. First, I apologize. you evolve to a final value which is lambda f. If you say t is equal to tau, t is equal to tau, then it goes to lambda f. Okay? Okay? Now, but you evolve with hf or lambda f, it is no longer time dependent, Hamilton. Okay? Now, so what is then important? Important in non-analyticities in dynamical free energy. I will define it for you, and then rate function of the return probability, which is logarithm of Loschmidt echo, which involves the double quenching process, as I explained. And then there are questions, does it have anything to do with equilibrium quantum phase transition, and so on. Many questions. There are more questions than answers, as you will see. So this is the simplest paradigmatic model where you have a transverse Ising model. Arnav introduced it. H greater than 1, one-dimensional model. H greater than 1, you have paramagnetic phase. H less than 1, you have a ferromagnetic phase, and two quantum critical points at H is equal to -1 and H is equal to +1. In the process of my discussion, I will involve both of this, and I just mentioned studies have been generalized to various integrable and non-integrable models, and I will just stick to this, and this is the reference which Diptiman also mentioned, where we talk about all the variants of these models and their quantum criticality. Okay, so what is the basic idea with which Heil, Polkovnikov and Kehrain came to this problem? I will go through very quickly, that if you look at the canonical partition function in a classical phase transition, Fischer's idea was generalized to complex temperature plane and look for the zeros of the free energy in the complex temperature plane. When your line of zeros cross the real temperature axis, that's your phase transition point. So simply generalized to complex temperature, you just put the lines in the thermodynamic limit, put the zeros of free energies. In the thermodynamic limit, the zeros will form a line, and you see whether the lines cross the real temperature axis. The point it does, it's your critical point. The idea is similar quantity you look at here, which I said Loschmidt overlap. So what you have, psi 0 lambda I, I'm referring to sudden quenches now. It is the ground state of the initial Hamiltonian H lambda I. Let it evolve with the Hamiltonian with the parameter lambda f achieved through a sudden quenching of the parameter, and look at this quantity. And now generalize time to complex thing, as it was done by Fischer in the context of classical phase transition, generalized to complex temperature plane. Here you go to complex time plane, where real part gives you the partition function, imaginary part gives you the time evolution. Okay? So what is the trick? Thermodynamic limit, you define a so-called dynamical phase dynamical free energy, which is, there should be all should be mod. So you look at this evolved state, overlap with the initial state, take the log and divide it by the number of systems, number of sites or number of spins. You define a dynamical free energy, look and defined in the complex plane, look for the zeros, okay, which are called Fischer zeros. So your zeros of the partition function, which is this fellow, zeros of the partition function immediately leads to singularities in this Fz, but they are all in complex plane. Only when your real part is 0, that means you are lying on the real time axis, they are observable non-analyticities, and this is reflected in this quantity. So idea is, you write down this quantity, which was with IT, generalized to the complex plane, look for the zeros of this quantity, which is the partition function, and then you will have singularities everywhere in the complex plane, wherever it is 0. But as soon as it crosses the imaginary axis, real part is 0, then you get back your IT, so it is reflected in real time. I will show you some pictures. Please. Yeah, this is complicated. I will tell you over tree. This is something called boundary partition function. You have a d-dimensional quantum system, and then you can think of classically a d+1 this. these are the boundary states of two layers. Okay? Okay? These are boundary partition. Okay? Now this is the Fisher zeros, which Heil, Polkovnikov and others plotted. So you plot, this is your phase diagram. You plot it from quench, the initial field was probably here. You quench it to the ferromagnetic phase, cross the quantum critical point and see the flow of Fisher zeros. If so, if flow the Fisher zeros, they nearly form a line. Okay? They are very closely spaced points, form a line. You can join them and you see they cross this point. If you draw a vertical line here, they cross the real zero axis. That means on the imaginary axis, these are your dynamical phase transition points. If you don't cross the quantum critical point, they don't cross the real zero axis, okay, and you don't have a dynamical. And if you plot the IT, which I defined, they actually shows cusps, prominent cusps at this real time when these lines of Fisher zeros cross the imaginary time axis. Okay, so this is the essential picture of dynamical phase transition. So to summarize, across the quantum critical point or equilibrium phase transition, lines of Fisher zeros cross the imaginary time axis. As corresponding times, non-analyticity appears in IT, which are here, and these people call dynamical phase transition, but I will like to call them as just non-analyticities appearing in real time. If you do it within one phase, Fisher zeros do not cross the imaginary time axis, no non-analyticity, DPTs are absent. But this is not watertight. We have shown there are many, many cases where you need not cross quantum critical point, still you will see dynamical. No, I will come to that. All you need, you have to somehow get a particular momentum more for each which you have excited state probability and ground state probability for a two-level system equal to half. That means effectively an infinite temperature. Okay. Now this dynamical phase transition actually was first observed, though they didn't claim it, by Subroto, Polman, Green and Moore long back in 2010. What they did, they took a generalized version of the Ising model which I introduced. If you set G is equal to 0, it's the critical transverse Ising Hamiltonian, one dimension. If you put phi, you see it is in a skewed field. Okay, the skewedness destroys the non-integrability, may destroy the non-integrability. Phi is equal to not equal to 0, phi not equal to pi, then it's non-integrable. But phi is equal to 0 and pi, then again it's a simple integrable transverse Ising chain. And then what they did a quenching. So they quenched G as Gi, Qf minus Gi T by tau. After a time tau, we reach Gf, and then look at the evolved state. You reach a state with Gf tau and evolve with it with the final Hamiltonian, and they looked at the rate function. Okay, so same prescription. Quench, prepare a state. Quenching here, slow quenching does give you a desired state. That's the role of quenching. Okay, look at the overlap and corresponding rate function. You look at the rate function. The definition in their case was with a minus sign. Remarkably, there are cusps which I showed and which actually re-derived by Polkovnikov, Heil and others. So there are singularities. These are people called dynamical phase transitions. On the other hand, if your value of the parameter phi is not 0 or pi, it's a non-integrable model, and they found there is no non-analyticities, everything is smoothened out here. So there was apparently it seemed that non-integrability destroys these non-analyticities, but I don't know, it may not be the case always. We looked at the antiferromagnetic version of this model, changed this interaction term just to antiferromagnet, and that has a rich phase diagram. In some cases, we found that even in the non-integrable situation, one may have that. But this is a different story which I don't want to go into. Rather, I want to stick to the simplest possible situation. Once again, go back to transverse Ising model. integrable, reducible to two-level problems and do a quenching, slow quenching, and see what happens. So there. Oh, we have not, in our DMRG, we have not seen anything other than T by tau. So I cannot comment on that. Okay, but integrable case, I can tell you whatever quenching protocol you know, I have the answer. Okay. So rate function of the return probability, this is your transverse Ising model written in every momentum mode. It's decoupled to 2 by 2 problems for every momentum mode. Change H as T by tau. I have two colors for T. First one is you are preparing a desired shape psi f and then calculate, let it evolve with a time. Once you reach this state, T is 0 again and you evolve it with the new time, adjust unitary evolution and look at the rate function. So evolution in rate starts after the quenching process is finished. So psi kf gives you this one. So Vk and Uk has the information, it carries the information that it has been quenched. Okay, so it is no longer a ground state of the final Hamiltonian. Okay, so you expect a very non-trivial dynamic. You calculate everything, everything can be calculated. You calculate the rate function of the return probability, you define the dynamical free energy and calculate the transition probability. What is the transition probability? That this is the ground state of the final Hamiltonian. This is the excited state. Final, I mean this is HF, where you reached after the quenching, and you ask the question, what is the probability? It is in the ground state, and this is the probability. What is the probability? It is in the excited state. So excited state probability UK, that plays a major role, which I will show now. So transition probability, that can be calculated. I believe Diptiman did this. This can be calculated. And this pk, when you plug that in here, you get an expression for dynamical free energy, which is given by this. Okay, again defined in the complex plane. Now go back, write the free energy in the following form, claim the non-analyticity, setting the argument of log to 0, and you can find out what is Znk. This Znk gives the expression of Fisher zeros, I will show. And now you can have a particular K star. This is the expression for IT. Now I have come back to real time, substituted everything in the real time, and I have looked at what are the values of T I can have non-analyticities. You can see there is a K star, particular momentum mode, for which Pk star is equal to half. This is so-called infinite temperature state I was referring to, and these are the corresponding real-time instants where you will have these Ks. Yes. Well, it's a misnomer. I am talking about a zero temperature problem. But in a classical statistical mechanics, two-level system, it refers to infinite. Okay. So this is the flow. You quench from paramagnet to ferromagnet, start from here, goes here. This is your lines of Fisher zeros, cross this particular axis, imaginary axis. This should be your dynamical phase transition points, reflected here, follow the rate curve. This is the dynamical phase transition point, and I have given the expression for Tn star. But interestingly, when you go from paramagnet to paramagnet, you are crossing two quantum critical points. One is here, one is here. So you see your Fisher zeros actually starts from infinity and then forms a loop and go back. So everywhere time you do a quench, I was having a Tn, but correspondingly when you cross the two quantum critical points, you will have two non-analyticities corresponding to each n. Okay, we call it Tn plus and Tn minus. H minus 1, to cross this particular H minus 1, that happens at Tn plus, and Tn minus 1, the other quantum critical. So Fisher zeros pick up the fact that you have crossed two quantum criticals. Why so? You just put Pk versus Pk, I said, probability of the ending up in the excited state at the end of the quenching. When you prepare your desired state, what is the probability that you have reached an excited state? That is Pk, Uk square. If you cross a single one quantum critical point, you see there is a 1 Pk. a K star here. When you cross two critical points, your PK, excitation probability, it's frozen at both K is equal to 0 and K is equal to pi, and you have two K stars. When you cross one critical point, by choice, it could have been K is equal to 0, but I chose K is equal to pi to be critical mode, which is frozen. Okay? So, there are two K stars. Now, last 10 minutes, okay, I want to tell you what is the emergent topology. It's first studied by Marcus Heil and Budich, and then we generalize it to full glory, and we'll show you what is the interesting behavior. So what people talk about, that it's a quantum non-cyclic evolution of the system, and best to study the Pancharatnam phase. Okay, so also we can call it a dynamical topological order parameter. I told you that there is no local order parameter, but there could be a string operator type of thing, a topological order parameter, and that really happens. So, characterizes topological properties of the real-time dynamics rather than of the instantaneous wave function of the instantaneous Hamiltonian. Changes its value, this is the property of this topological order parameter which I am defining, changes its value at every dynamical point whenever you have non-analyticities in Loschmidt overlap. So how do I define this? Let's recall psi kf, which is the state I reached after the quenching. This is the state which will evolve with the final Hamiltonian. This state was like this. So define after evolution with the final Hamiltonian for a time t, define this quantity Lk, which I have already defined. It's a complex number. Extract the real part and the imaginary part. This phi k. But this phi k I cannot call as a gauge invariant quantity. As you do in the very phase, you have to get rid of the dynamical part. And dynamical part is like this. So this helps me in defining a geometric phase, which is phi k, which comes out just writing the Loschmidt overlap in the following form, and then define the phi k time. In more formal language, you are actually going to the ray space from the complex space, space of density matrices, and this is actually defined in the space of density. Now, interesting point is, as k goes from 0 to pi, your real Brillouin zone, this fellow shows an winding, it goes from minus pi to pi pi, and thus completing a full circle modulo 2 pi. You can ignore this. I state k star is an important parameter. You remember what is k star? K star is these set of momentum values for which you get pk star is equal to half. Correspondingly, you see non-analyticities in your free energy. Okay? So that k star value, you can write what is this Pancharatnam phase, and you will find out it has a form like this. At dynamical phase transition, this quantity is ill-defined. And if you look at this color plot, which shows the variation of dynamical phase, this axis is lattice momenta k, this axis is time. You can see that winding increases as you go in time. Every time is cross a dynamical phase transition, you have one more winding. Okay? That immediately tells us that probably this fellow, if I define this fellow integrated over Brillouin zone scaled by 1 over 2 pi, you can think of a generalized Gauss law. This may serve as an order parameter by showing integer jumps at every dynamical phase transition. Okay? So you can look at again at the point k star, and I'm not sure whether it is clear from here. It actually alternates between 0 and pi at every dynamical phase transition. The phase, geometric phase at k star alternates from between 0 and pi at every dynamical phase transition. Okay? So if you look at probe k star very closely, you have two pieces. Okay? This quantity will diverge at every dynamical phase transition, while this quantity will increase monotonically or decrease monotonically. That tells you something important which I show in the next. So, nu d versus rate function, nu d and rate function as a function of time, Pm, which is actually non-topological. If you map this problem to the Majorana chain problem, okay, That's why I'm calling it topological and non-topological. Paramagnetic phase, there are no age minors if you think in terms of the corresponding POF superconducting chain. So if you quench from non-topological to topological or simply paramagnet to ferromagnet, you simply see these two terms I am writing here conspire, and they conspire to give you fantastic step-like structure. These are your dynamical phase transition point. You see this order parameter, this topological order parameter senses every dynamical phase transition and jumps by a step of unity. Okay? So this characterizes this dynamical phase transition by changing every time by a step of unity. And you see here goes down. Here in this picture it goes down. What did I change? I changed the direction of quenching. In the first one, I came from -10 deep paramagnet to ferromagnet. In the other one, I came from the other side. So if I remind you this picture, first picture I came from this to this. Second picture I came from this to this. Okay, that changes my direction of quenching. And how does it change? What does it change? Here you see Piquet star was here. In the next one, if you come from this to this, you will see it will be a reverse picture, mirror image, where you will have UK square is equal to 1 at K is equal to 0. So slope changes. Here slope is positive. Here slope is positive. UK square, this slope is positive here, and that gives you a step which goes up. And if you do the other way around, the slope will be negative, and you get a decrease by a factor of unity at every dynamical phase. So this is for quenching a single quantum critical point. Far more interesting thing here, if you go to two critical points, you see what happens. I remind, it is there already. Don't go back. So every quench, you go from paramagnet, ferromagnet to paramagnet. This picture I should have given here also. So you paramagnet, cross the ferromagnet, go to the paramagnet. Okay? So what do you expect? You have a lobe-like structure, which I am showing. Okay? I have given a plus minus every one. That means topological charge of these dynamical steps will be +1. It will be immediately followed by, see, each lobe corresponds to two non-analyticities, I told you. One will carry a charge +1, other will carry a charge -1. See, this pattern goes on. So what you will see, there is a jump immediately followed by a fall. So there is an oscillating pattern of this order parameter. First one gives you a up when topological order parameter is +1. I will explain in the following way. As I wait, positive charges are entering system. Immediately after positive charge, there is a negative charge, making it down to 0. Up to this point, everything is fine. So you see plus minus pattern follows. But again, suddenly you see a jump by factor of 2 at some point. This took us some time to understand. Then we analyze these Fisher zeros very closely, and you can see sometimes two successive positive charges can come because of the structure of Fisher zeros. Whenever you have two successive positive or +1, you mean two positive charges are entering. So you have a jump by a factor of 2 because you have two successive dynamical phase transitions with two positive topological charges, and then this oscillating pattern follows. So what we have found out that both sudden, which was initial idea, and for a slow quench, I remind you what is the purpose of doing a slow quench. Purpose of doing a slow quench to get a desired state, and depending upon your rate, as Subroto was asking, depending upon your rate, depending upon our protocol, you reach a different state and then evolve it with your final Hamiltonian and see how the behavior changes. You will find out a beautiful topological pattern emerging. At the same time, you will see dynamical phase transitions, and importantly, all these dynamical phase transitions are characterized by topological order. So that brings me, and I explained to you, the slow quench gives me the possibility of studying, which is very important. If you slow quench gives me the possibility of studying crossing two quantum critical points, one can show if you do it suddenly, then you go from this paramagnet to paramagnet, jumping through this ferromagnetic phase, all the properties are lost. Okay, slow allows you to do that. Okay, so that brings me to the end of my talk. I will summarize. Apparently, there exists a new class of phase transitions, again with my reservations. One should talk about universalities, diverging length scale, a new class of dynamical phase transition happening, which shows up or manifested in the real-time unitary evolution of a closed quantum system following a quench across a quantum critical point, though there are exceptions, known as dynamical phase transition, reflected in the non-analyticities in the rate function. Integrable models, Fisher zeros, DPTs for slow quenches, topological order parameters can be associated with the existence of DPTs in slow and sudden. So it's emergent because it's coming out of the quenching, and I'm extracting the topology from the quench system, and numerous open questions, as I said, higher dimensions. If there is a topological model, Hurlin model, how that model topology influences the existence of this topological behavior, and then universality, diverging role scale, role of integrability. I showed there are already contrasting results, and especially experimental signature. So far I know, Loschmidt echo has been experimentally studied, and people have seen the dip in Loschmidt echo at the quantum critical point, but unfortunately it's still then with 9 speeds. Okay, so it will take some time when people can really see whether these dynamical phase transitions can be experimented. Thank you very much.